In a previous video, a very important theorem was introduced linking the stability of a system with the integral of the impulse response absolute value. And in this video, I'm going to apply such theorem to simple systems. And by doing so, we'll begin to grasp the relation between the stability of systems and the position of their poles. So let's begin with a unit gain first order system. 1 over S over P plus 1. Now, if we want to calculate g of t, we need to apply the inverse Laplace transform to this. Maybe it is more convenient to multiply both numerator and denominator by p to get p over s plus p. And with that, we can apply the inverse Laplace transform, and we get that g of t, well, I'll write g of t here, g of t is equal to p times e to the minus pt. This is the impulse response of this first order system. Now, if the pole is in the left half plane here, if minus p is less than 0, then the output, the impulse response g of t, is equal to, well, if t is equal to 0, then the only thing we have here is p, but p is positive, so we begin here. And now as time passes, as this exponent grows, this term tends to 0, tends to 0. So we have this exponential. Now, if we apply the integral, if we calculate the integral, we get this area under the curve. And obviously this area is finite, which means that the system is stable. However, if the pole is in the right half plane, if minus p is greater than 0, which means that p is negative, then we would start from this point here, and the exponential function would grow without bounds. And this area here, the area under the curve, remember that it is positive area because we're using absolute value, well, it cannot be calculated. The integral doesn't converge, and therefore the system is unstable. And in the limit situation with the pole here, what we have is actually g of s equal to 1 over s, and we already know that the inverse Laplace transform of 1 over s is just the step function. The step function has this shape, and as you see, the signal doesn't grow beyond certain limits, beyond certain bounds, but that doesn't matter because the theorem is related to this area here, and this area is also infinite. The integral doesn't converge, and therefore the system is unstable as well. But since this function doesn't grow beyond certain bound, we call it marginally stable. But remember, marginally stable is also unstable. Is it is in the limit, but it is unstable. Okay, let's go now with second order systems, and I'll do the calculations for a system with complex conjugate poles, because if we had an overdamped system, a system with two real poles, we could use the analysis above. So in general, if we have a couple of complex conjugate poles, g of s is equal to s over p plus 1 times s over p conjugate plus 1. And we know that this could be written as p times p, well, we only need to multiply by p times p conjugate to get s plus p and s plus p complex conjugate. And this, remember, that led us to, well, among other things, to write this as omega n squared. This is p times p complex conjugate times over s plus 2 times the damping factor times omega n s plus omega n squared. But in order to find the g of t, we start with this equation, with this transfer function. This is equal to certain residue over s plus p plus the complex conjugate of the residue over s plus p complex conjugate. So let's calculate now r. R is equal to p times p conjugate over s plus p times s plus p complex conjugate, everything times s plus p, and we assume that s is equal to minus p, which is equal to, this cancels out with this, and we get p times p complex conjugate over minus p plus p complex conjugate. Okay, we already know that this is omega n squared. Now let's draw the positions of the pole. Let's draw that diagram I told you you should learn by heart, with the poles, with the two poles here at minus sigma plus omega d, j omega d. And remember that this distance is the natural frequency omega n, and this angle here is theta, and the cosine of theta is zeta. So this term here is omega n squared over minus sigma minus omega d, j minus j omega d, plus sigma minus j omega d. So this goes with this, and we get omega n squared over minus 2j omega d. But according to the diagram, omega d is equal to omega n times the sine of theta, of theta. And this is the same as omega n times the square root of 1 minus the cosine of theta squared, the cosine squared. And this is the same as omega n, the square root of 1 minus theta, zeta squared. Or Or in other words, omega n squared is the same as omega d squared over 1 minus zeta squared. And we can apply this here in order to finally get our expression for the residues. This is omega d squared over minus 2j omega d times 1 minus zeta squared. And this cancels out with this 2. So we get omega d over minus 2j omega, no, minus 2j 1 minus zeta squared. Now I'm not going to calculate R complex conjugate, but it is omega d over 2j 1 minus zeta squared, just the complex conjugate of the previous residue. So we put those results here, and we find that g of t is equal to omega d over 1 minus zeta squared times 1 over minus 2j times e, this is the first residue, e to the minus pt plus omega d over 1 minus zeta squared times 1 over 2j e to the minus p complex conjugate t. But these two terms can be written e to the minus sigma t e to the minus omega d t, and in this case e to the minus sigma t e to the plus omega d t. So applying that, we find that g of t is equal to, we take out the common factors, omega d over 1 minus zeta squared times e to the minus sigma t. This is the common factor, and now this is minus e to the minus omega d t over 2j plus e to the omega d t. And applying the Euler's formula, we know that this is the sine of omega d t. So g of t is equal to omega d over 1 minus zeta squared e to the minus sigma t, the sine of omega d t. What does that mean? That means that if our poles are in the left half plane, that is, if minus sigma is negative, if we have the poles in this side of the plane, then this is a decaying exponential. This term is an exponential like this, which is multiplied by this sinusoid to yield the output, which is something like this. This is the multiplication of both, so we would get some signal like this. And in this signal we can apply the integral, and we find that all this area plus this area here plus this area plus this area and all the areas, finally the sum of all those areas finally converges to certain value, and therefore the system is stable. But if the poles are in the left half plane, sorry, in the right half plane, so minus sigma, the real part, is positive, then we would have the multiplication of a growing exponential times the same sinusoid, and this is something like this. So this would be the output, and obviously if we start adding up all those areas from 0 to infinity, we don't get to any value, because it keeps growing and growing. So the growing and growing, so the integral doesn't converge, and the system is unstable. It is unstable because the poles are in this side. Finally, if the poles are in the imaginary axis, well, that means that theta is equal to pi. So the cosine of theta, which is zeta, is equal to 0. It is 0. And also sigma is equal to 0. There's no real part. So here we would have 0, and this would be 1. E to the minus 0 is 1. So our g of t would be simply omega d times the sine of omega d t. Or, in other words, just this signal here, this sinusoid. And just as in the first order system, the signal doesn't grow beyond certain limits. But if we add up all these areas, we can't find a value. The integral keeps growing, and therefore the system is also unstable. But because the signal itself doesn't grow as it happened here, we call it marginally stable, which is just one category within unstable systems.